Hi, Bill here. If you watched the previous video, we almost got started on the metal lathe when I discovered a broken gear in the gear train. So we had to take a bit of a break there, fix the gear, put it back in. So this is, in a funny way, a bit of an engineering life goal to copy a gear. A year ago, this would have been quite a bit harder than it is now. With a 3D printer, this is comparatively quite simple. So I'll walk you through the steps to replicate this gear and just what's going on inside the machine that led to that failure. So let's get started. I started up the metal lathe and it's been a while. I've done some different projects on it. I haven't threaded anything in quite some time. And when I turned it on, I heard a kind of a clunking sound. It sounded like the gears weren't quite meshing. And these things are really greasy, so I'm just trying to hold it here, but I don't know if you can see this edge crack here. So the nylon gear broke at that point. And maybe the quick backstory here, I'll show you what the gear train looks like, but these nylon gears are designed, if there's anything that jams up in the transmission, the nylon gear is designed to break before you strip your transmission and ruin the machine. So this gear has a very important function, and I can't even remember when this happened. So this was years ago. I don't remember specifically. At some point this broke, and it won't cut the threads right now because the force opens that just a little bit and it'll slip a tooth or two or three. So if that happens, the threads will get off each cycle. Just not a good thing. So mission number 2, build a new gear. I've thought about it. There's some good YouTube videos on how to make gears on the lathe. It's a little bit to set up, so maybe the subject of another video. But more recently, I picked up a 3D printer, and this seems like the perfect exercise to try and copy a gear and print it on the 3D printer. So, kind of by way of introduction, if you had to copy this gear, let's say, thought experiment, what are the important measurements that you'd want to write down? Say, what's the minimum amount of information we'd need to copy this gear? So do you think we can do it in three measurements? 1, 2, 3, 4, maybe 5. So I think the obvious one would be outer diameter. So I'm thinking we probably need 3 diameter measurements, a thickness measurement, and a number of teeth. And then depending how complicated the tooth profile is, we may need more measurements around the teeth. But let's start simple and see how complicated it needs to get. When I was thinking of labeling these, the first thing that came to mind was small, medium, and large. That's maybe a little bit simplistic, but we sort of have this large dimension here. The medium, I would say, is sort of the thinner inner edge here inside the teeth. So we'll have a slightly thinner one, and then the hole in the middle, and there's a sleeve, a metal sleeve I'll show you that fits in there. So we've got Machinery's Handbook 20th edition here, and I thought rather than small, medium, and large, we could look up the definitions of these gear terms. This was more complicated than I thought. There are 4 pages of definitions here, and some of them that are pretty close. So I think if we go with base circle, the circle from which an involute tooth curve is generated or developed, we can get the diameter there. And then if we go over to, what did we have here? The root diameter, or the root circle, so the tangent to the bottom of the tooth spaces. And the difference between the base diameter and the root diameter will be the hole depth, so that's how much we want to cut in. And then we'll go with internal diameter for the hole in the middle, and let's go with width for the width of the gear. So if we start off simply here and get some measurements. So the easy one from our definition, the base diameter here. So if we measure on the outside, the widest part of the gear here is about 1.823. And a little bit more challenging if we go this way and try and catch kind of in between two teeth. And I'll do this a few times just to make sure I get the two adjacent teeth. So I've got about 1 point. What's that? Come in here. So it's about 1.672. So about 1.672. And then if we go on the inside, okay, I'm just going to push it around a little bit to try and get a nice, say, 0.77. Sorry, 772. And we'll get thickness. So that's about 383. And this one has 45 teeth. So an even tooth gear is just a little bit easier to make. So odd tooth gear will have an extra surprise. Trying to fit that extra tooth in, but easy enough to do that. So I think that's what, if I went with those 4 dimensions, and it's not a crazy gear tooth profile. It's a little bit, it's not quite so simple, but when I look at it, I kind of see this shape, maybe with blunted ends a little bit. So since I'm going to draw this in CAD, I'm going to try and get it close. You could also try and come in here and measure a tooth, and it might be a useful number. So it's somewhere around 0.06. But that's a tough measurement to grab with the calipers. So we'll see 1, 2, 3, 4, 5. So I think those 4 measurements and the number of teeth gives us a pretty good starting point. Now, I do miss the really nice CAD packages I've used in previous roles, but for this one, I went with the free version of Tinkercad, and I was really impressed with what it was able to do. One thing that's a little unfortunate is I think I can only work on one project at the time in this format, so I saved the gear I made, and I went on to another one. So this is basically what I did, but this is a 30 tooth gear. So essentially mapped out this little piece of rice looking thing for the gear, shaved off the edge, and kind of rounded it with a donut shape. So sort of 3 shapes here. This one here, the solid shape, was the minor diameter. So that was the 1.672. And I cut a hole in the middle with this whole cylinder to the 0.772 dimension. Then I modeled these gears and replicated kind of a opposing pair, and then copied those going around. And for the 45 tooth gear, I had to pay a bit more attention to the angles and add that extra one in. So there were 45. Odd number is a little bit trickier. The even numbers, they tend to be a bit quicker to draw out. So that's essentially, and then the height here. And then for this gear, I just added sort of this donut shape on the outside to try to just round, I don't know if you can see that, round the teeth a little bit. But like I said, I seem to have lost the Tinkercad file for the 45 tooth gear, but I do have what I downloaded in the tool I can edit. So this is what the 45 tooth gear looks like. and we can open that up, open up that STL file. So here's our 45 tooth gear in Utilamaker Cura. Again, really nice free toolpath or G-code package that takes this shape and breaks it down into instructions for the 3D printer. So each of the lines that it has to draw out to make this shape. So when you're ready, slice it. I'm using a 10% infill. You could make this completely solid if you want. I'm going to use PLA, polylactic acid, and there's quite a bit of strength in it, even with, say, a 10% infill at a standard quality 0.2 millimeter, sort of the smallest element you could resolve. It's a good level of detail for this. And the odd thing about this gear is I kind of do want it to break before the steel ones, so I don't want it to be too strong. I want it to be able to keep its shape and keep the kind of the sequential representation as I'm threading, but I don't want it to wait too long if something does get jammed. So I felt like a 10% infill was reasonable. And then you slice it, and once it's ready, all the G-code is produced. We'll pop it into the machine and see what happens. Okay, so let's see how close we are here. So for the base diameter, we were looking for 1.823, and we've got between 1.812 and 1.815. That's pretty good. And for the root diameter, we were looking for 1.672, and we've got 1.661. Internal diameter, we were looking for 0.772, and we've got 0.758. And for the width, we were looking for 0.383, and we have 0.391. That looks pretty good to me. So let's press the sleeve in and install it and see what it looks like. And this is the press where I can line up the gear and the sleeve, and I can drive that down and push the sleeve in. Well, I got pretty excited holding that gear in my hand and completely forgot to film pressing the sleeve in and installing the gears in the gear train. So here's the one we just printed. It's working great. The steps to commission this gear I thought would make this video a bit long, so I may break those out into a separate video. I didn't just turn the machine on once this gear was in. I want to make sure that it was working pretty well. So there are a few things I did there, and we also came across the decision to replace these gears as well, and so I'll talk a bit about that in the second video if you're interested. So hopefully this gives you some idea of what's involved in replicating a gear and installing it in the gear train. Thanks for watching.